Okay, so before I start today's class, so let us recapitulate, start from where we have started, we have stopped. So the point where we have stopped is that you have learned about the this oxidation state, stability, and all these things a little bit, and then we have come to the metal and ligand part. So definitely what we know that these metals are the transition metals, because we are interested about transition metal and their complexes. And to make a complex, definitely you need a ligand. Now this ligand are what we have seen, that the ligands must be Lewis bases. So if a ligand is a Lewis base, and definitely one thing I just forgot, and not forgot but I missed maybe, that this metal ligand bond, this metal, one metal and one ligand, and how do they make the complex depends definitely on the compatibility of the metal, that particular metal and that particular ligand. Like you have read this hard acid base concept, right? So hard actually combines well and this more stable, and then hard, the soft is more stable. Exactly like that, these metals and the ligands also, they have the this affinity for someone. So how do we know that this particular metal ligand complex is stable? So to understand that a metal ligand complex is stable, what we do, we go for the stability constant, right? So the stability constant, and so for a particular reaction you can calculate the stability constant, I mean, for a particular metal ligand things. And then we will discuss a little bit about the thermodynamic parameters, and how these thermodynamic parameters actually controls that stability also, that we will also see a little bit, right? So let us first take what we do as stability constant. So this understanding stability constant, what we have done, okay, so you have a metal, and you have, let's say, metal in, okay, so you have metal H2O, let's say we have taken 2 plus, and we want to replace it with the air. So the first step is that MH2O whole 6 2 plus plus L, right? So in that way, I shall definitely not write all the steps, and in the last steps definitely, so this is the last step. Now this individual, this constant, okay, another thing I have to tell, individual constant, there are two type of stability, right? The stability is one, I mean, it must be that. So there are thermodynamic stability and second is kinetic stability. So don't, it's not, we will not, I mean, go very detailed. So what is thermodynamic stability? From the idea, you know that thermodynamic stability is that whether the reaction will go and proceed to the formation of the complex or not. I mean, whether the complex will be ultimately stable or not, that is determined by the thermodynamic stability. So, or the extent to which the complex will form. So, I mean, we can tell that extent to which the complex will form. In that way, we can complex will form. Now, the kinetic stability, what does it say? Kinetic stability say that what is the speed? I mean, let's say you have M formation of ML16 and you have ML26, right? So if you can attain, I mean, during the reaction, so let's say you have started from MH2O6. So in a reaction, if you can attain one of them first, then the second one, then you will say that this is more kinetically kinetic. The speed is more, but whether this will form or not, and even if they form, how much stable they are, all these things will be taken care by the thermal stability. So you know that is just here. I mean, I'm telling you. So there are 6 steps if you just go through this. So I am not writing all the steps and K2, K3, all these things. So these are called stepwise. This K is called here stepwise stability constant. Yeah. And if you just go, this beta is equal to, it is taken like this, overall stability constant. And in that case, this beta 6 is beta, let's say here it is 6, so K1 into K2 into into K6. Right, so this beta value, sometimes it is given, and then, and if you do the log of beta 6, you can know that what will come, log of K1, log of K6. So this is just a representation that how do you measure the stability. Someone wants to join again. Yes. It's 9:17. Please maintain the time at least within 15 minutes. So this is the stability. Now, if you remember, let us again do a little bit of explanation. So, in what context we were discussing this? If you remember the context, that if you have a metal and if you have a particular ligand, so there are monodentate ligand, bidentate ligand, tridentate ligand, we have seen that there may be different type of ligands. So do these monodentate, bidentate, all these things, how does they affect the stability? So what we have learned, that if there is a chelate ring formation, then the stability of the complex is more. So if there are chelate ring formation, so in every case, does it the same? I mean, in every case, every chelate, is it the same stability? Or how does this stability is affected? So we will just look it in a very simple manner. We will not go to very difficult things. So if you just think of a reaction, del G0 is equal to del A0 minus T del S, or I shall not write the 0. So this is the thing that you have learned for a long time, and very, I mean, easy way we will see how does this happen. So, uh, okay, let us take one example. Let us take NiNH3 whole 6. Now NiNH3 whole 6, and this is called ethylene diamine, right? Now if you just take NH3 whole 6 plus En, so in the first step, plus 2 or if we just consider that right now, if we look at that particular reaction, what do you see? That this nickel is bonded to the same nitrogen, and if you look at these two ligands, this one NH3 and these two, so a little bit of change in the Lewis acidity character must be there, but that is not too much when they are joining to the nickel. So now we will just in the stability context, we will see that how does this del H value and del S value are affected. Now this del H value in very common sense, I mean, if you if I may be a little bit wrong, but I am just writing it. You please check it. I shall also check that for that reaction, the del G equal to minus 67 kilojoule per mole, roughly. I mean, it may be a little bit odd. Now if you look at that part, then calculation has shown that the del H has taken care of this 13 kilojoule per mole and the stability, and the rest is, that is 54, right? This 54 minus 54 kilojoule per mole has been taken care by the entropy factor. Now, very roughly said, the enthalpy of this type of reaction, what are the, for this metal complex reaction, who take care of this enthalpy? The enthalpy is taken care by the bond strength, then heat of hydration, then crystallization. So these parameters, etc. I mean, I'm not telling you too much because for that particular you really don't need that much. So I just want to make my point clear. So these are the things that actually uh, take care of the part of enthalpy. So there is, as I told you, that NH3 and this NH2, definitely a little bit of change is there, and this nickel forms this bond with, when the bond is breaking and all these things, and then this is mainly the part. But if you look at the character of this, like whether NiEN3 is a very different compound from NiNH3O6, no, but it is more stable. So the main factor is the entropy. So entropy also has a lot of things that contributes to the entropy change. But what we can see, and particularly what we will consider for the chelate formation state, is that the number of molecule, the chaos change, because here the number of molecule is 7 and here the number of molecule is 4. So it is going for 4 to 7. So the entropy uh, is the factor that we will consider for the chelate formation. But try to understand that if somewhere given, I mean for some tricky question, that this reaction, the del G is positive, but you can see that the chelate ring is also forming. So then please don't look at only the chelate formation. And again I am coming that not only the chelate formation, and the stable chelate is also a factor, right? So now this is the point, the first point that says that the chelate formation actually stabilize a complex. So now this the term always called the stable. The first thing is that chelate formation. Okay. The second thing is that if a chelate is formed, what are the things that actually uh, I mean, contribute. So there is a term called bite angle. See, all these things are there in the slide. I mean, but I am just explaining and I shall show you that. So what is a bite angle? So what do you mean by bite angle? So if you have, let's say M, so there may be ligand like this. There may be ligand like 1, 2, 3, 1, 2, 3, 4, 1, 1, 2, 3, 4, 5. So 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4, 5. And then you can have right. So there are, so if you take this, then it will be a, so it will be a 1, 2, 3, 4. So it is a 4 member, right? Then if you take this, then it is a 1, 2, 3, 4, 5, 6. Sorry, 1, 2, 3, 4, 5. So this is a 5 member. And if you take in that way, it is a 6 member, and this is a 7 member, right? So now if you put it like that, so one is the size, the how many members. If you go for the stability, then it is this 4 membered. So 5 membered is the most stable. So I am coming to the bite angle, then 6 member. But the point is that generally the 5 membered chelate are more stable. But if the 6 membered chelate have a ligand that is conjugation is there, then as you know that the principle of this resonance, then this in case of ligand is conjugated, then the 6 membered chelase is more stable than 5 membered one. But otherwise, if there is no conjugation, like ethylene diamine you do not have any conjugation. So in that case, the 5 membered ring is the most stable ring. Now what is a bite angle? So the bite angle is, here you see, this is the bite angle, right? So I have written all these things, you just read when I shall give it. Okay, so this is the bite angle. Now if you see that this bite angle is related to the strain of the system, like how much strain will that particular, all these things are written, I am just trying to explain you. So how does it happen? So these angle actually is depend on, I mean whether you this is a very compatible situation. Like here you just see that there is a ligand bite, and if this M is like this. So now if this bond length permit, so in 5-membered ring this bond length permits the best. I mean there must be a bond n to l bond length that is the in the most stable case, and in most stable case the bond angle is 5-membered is the stable the most stable. Now the point is that you as I told you earlier that for the 6-membered ring, why does it the more stable when the ring is conjugated? Then you can remember that if you have a 6-membered ring, if you have a 6, then these angles can these bond lengths can change, right? So it can go right these and it might happen like these. So in that case, these bond angles actually can change a little bit when it is a conjugated ligand. And for that matter, actually, this if it is a conjugated, then it is a more stable thing. Okay, so I explain things from here. So if you have understood, please let me know. Otherwise, I shall uh, go to the next topic. Is it clear?
Yes, ma'am, it is clear.
Okay. So this is so there are things, I mean in the slides also that you can read, and if you do not understand I shall come back. So now let us come to the isomerism. So this isomerism, so the first question is that have you read the isomerism in second year or in your plus 2? Please let me know. Inorganic isomerism, have you read? Anybody in the second year or in plus 2? Even if you read it, I shall touch. Don't worry. Don't write in chat box because I cannot see the chat. Any response? Yes or no?
Ma'am, we have read about geometric isomers and optical isomers a little bit.
Little bit. So okay, I mean we will also discuss this, but first we let us tell. So I am not explaining, I am not wasting time on explaining what is isomerism, that you know. So if you have metal complexes, so we are only uh, interested about metal complexes, and these things as I can say to you that these things is not that you have to memorize or anything, you just have to find this isomerism, that also because sometimes is it required. So and mostly the diastereomers and enantiomers, these things actually mostly is relevant in the future. So if we just find define it, then there are two type of isomerism. One is structural isomerism and another is stereoisomerism. Isomerism. Okay. Now, if you just look at the structural isomerism, so what are the isomerism? One is, let me first make the list and then I shall go and give one examples for this. So the structural isomerism, one is ionization. Number two is there are okay, hydration. Then she is ligand isomerism. Number four is this coordination. Number five is polymerization. And six is linkage. So the examples I shall come linkage. And this one we will read a little bit more. I mean diastereomers, diastereomer, then enantiomer. That we will put a little bit of more effort. Today we will just go through this. This is so the first thing I shall say for the coordination complexes, this is not the example for a particular set. The coordination complex, the isomerism is sometimes is very important in terms of the functionality. I mean, if you remember that cisplatin and transplatin, so you just see at this particular molecule, other than the position of ammonia or chlorine, both in the trans position and the cis position, the both this compound is heaven and a little difference. I mean, not in terms of the quality. It is not the quality of the complex. I mean, heaven and a difference in terms of the activity of the compound. So cisplatin, as you know, this is very active for this cancer therapy, and you can just see what is the reason. So the position of the ligand and is very important when you are going to do some reactions with that. I mean, in whatever field, here it has been attached to the uh, DNA linking. So you can see that how this cis things is uh, I mean, is helping, because the cis thing is helping. Okay, one thing I'm sorry, I'm very sorry that I must have said that this macrocyclic. I mean, if you have this here, I am explaining. I mean, okay, in the slide maybe it will be somewhere. Like if you have M ethylene 2, instead of if you have a ligand like this, right? So if you have, so the six ligands are from the same thing, then it will again be much more stable. This is called macrocyclic effect. So if the metal is that, then it will be much stable depending on the bite angle and all these things. So this is called macrocyclic effect. And there is another thing that I have not explained here. I am telling, this is something you have to, I mean, it is said, it is not like you can measure it some way or something. It's not like what they say, that for a chillet, let's say for some reasons there is a bond breakage, so there is a bond breakage. But if you have, let's say, MNH3, your bond breaks and this ammonia goes to the solution. The story is finished. But if you have this ethylene diamine, even if one bond breaks, another remain in the vicinity, so it may pull within some time this NH2 again. So this is again, I mean, it's not like you can explain it with some parameters or something. So this is the feeling, or this is the understanding that happens. So here also you can see that you can say that if this is a platinum, so this can go to a 1 DNA and this can go to 1 DNA, but that will do a little more work. But the effect actually this gives, this is the outstanding effect, because platinum always the Cl bond dissociates and this uh, bonds to it. And here you can say that why this cisplatin is so important, and there are other compounds a little more active also, but all these things, even then the cisplatin is really very important, because this particular ammonia, maybe it is sterically less hindered, and all these things actually uh, gives the age for this cisplatin particularly. So this is the importance of isomerism. So when, if you be in the chemistry field, and if you be in the catalysis, you will see that this particular enantiomer that can do the catalysis, because when you are doing a catalysis, you know that you have to make a bond with another molecule that you are going to catalyze. So that gives you that helps you, that particular isomer actually helps you to perform the particular reaction. So this is the importance of isomerism in coordination complex. Definitely it is not just to read and these isomers are there and these are not, but these are the, and for that matter, really that stereoisomers helps a lot. Okay, so let us go to quickly look at this isomerism, this other isomerism, the structural isomerism. So the structural isomerism, the first I told you, the ionization isomer. So ionization isomers, from the name only you can know that if you have a reaction, I am just writing the both the isomers, then only you will understand. So in H3 it's very easy. So you have beer and okay. So for that particular case, if you look at that, then you must have one thing in clear. One thing is clear, and that I am not explaining because I know you people know these things, and even if you do not know, I shall tell later. This is the inner sphere, and this is the outer sphere. Right, this is called, I mean, in that way, because the particular thing in complex, though they contain the same number of metal atoms, same number of both the ligand, all the ligands, but they are different compounds. Right, they are, because once it is there, and also, I mean, if you just you can get a questions like this, like it's not that you someone will tell you that give two examples of ionization isomer. No, people will not give you like this, but people will give that this is the general formula, let's say. This is the molecule, this is the empirical empirical means this will again breaks up, the people will like N5 H15, so that way also people give. So this is the empirical thing. Now maybe this is a color A and this is a color B. So when you will learn the spectra, then you will see that depending on this ligand, the splitting in the T2G EG level changes, that you know a little bit. So I am telling, so that changes the color of the compound, and in that case you can say these two isomers are there. So these type of questions generally come, but until and unless you read the spectra, you will not face this question. But it's not that people will ask write two isomers, this ionization isomers, right? Now the next term is hydration isomer. So hydration isomer is actually a uh, uh, same thing like ionization isomer, but definitely it involves the water molecule, and for that reason it is called hydration isomer. So hydration isomer, what are the example? So H2O whole 4 Cl2 Cl. Okay, so this is the hydration isomer. Okay, now this structural isomer, this coordination isomer is that this is one type of coordination isomer, that this cobalt and the ligand exchange, I mean the change in the ligand. So this is one type of, and then there are another type that let's say take cobalt and cobalt. Let's say anything, I mean any particular. So this is the reaction, and then you have, let's say, NH3, 4, right? And then Cl, and then it has NH3, 4, NH3, 1, 2, 6, 1, 2, Cl, and then it might be next one is Cl3, Cl. So these are again very easy thing. And then the linkage isomer, if you take, this is, there is a term called ambidentate ligand. Like if you have NO, if you have NO2, if you have NCS, they can bond like MNO or MONO, or they can bond like MNCS or NSCN, or so this is called ambidentate ligand, and this is called linkage isomer. These two compound is called linkage isomer because the link is different. Okay, the next is the polymerization, because polymerization, the formula, empirical formula remains the same, not the formula. So if you just go to the others, then you will sorry. You see that formula remains the same. From this 1, 2, 3, 4, you can see the formula remains the same, but for polymerization, formula doesn't remain the same, right? And this is the ligand isomerism. Why it is called ligand? Because the isomerism roots from the ligand. So the ligand are, both the ligands are isomer within themselves, and then they actually form the ligand isomer in this case. So these are the, so there are differences of stability, actually stability differences there, otherwise they are the molecular formula is the same. So here one thing I must explain a little bit, as this is for, before I go to the, Okay, so one thing I must explain here that this ligand, so there is a term called innocent and non-innocent. Right, so there is a term for ligand which is called innocent and non-innocent. So what happens? So you have a M, and you may have M2 plus or 3 plus, anything you may have. So again, try to understand the concept. And you have a ligand. This ligand is L. When you are forming the complex, let's say M2 plus plus L, then ligand is coming to the complex as neutral ligand. It's not coming as a negative ligand. But after the formation of the complex, after the complex is formed, let's say after ML6 complex are formed, then if you study the reaction, what happens? You can, I mean, there are techniques. There are techniques like EPR. Uh, I shall explain a little bit of this EPR, NMR, all these things. So you can see that now this is in between 2 plus and 3 plus, and the ligand is also is not completely, ligand is not completely neutral, but it has also a delta negative charge. It's not delta, it's a little bit more than delta. So in addition to that 2 plus, the ligand is not behaving as innocent. So if a complex is ML6, if M2 plus plus 6L is ml6 2 plus and the whole charge is on the M, then it is called non-innocent ligand. But if a compound is after that 6 cell, it becomes ml6 and there is a charge separation, then it is called, sorry, non-innocent. So do you get the point? So do you get the point, innocent and non-innocent? I can see the chat, so you can write it. Okay, let me stop the presentation because I have not it ready for a time. Just a minute.
Hello, ma'am.
I can listen, please tell.
Ma'am, can the neutral ligands be regarded as the innocent ligands? Because here we.
No, it is not the term neutral, or I mean, it is, you cannot uh, specify a particular ligand as innocent ligand. It depends on the ligand. So when it approaches the metal, it is neutral, right? But as you can understand, the ligand is also a reactive thing. I mean, ligand is also there are polarization. I mean, when the metal and the ligand forms bond. These things you will understand when we will read very in the go to the deep into the uh, bonding. Okay, so then you will understand. So the concept is that when the you have a metal and the ligand is approaching, when the ligand is approaching, ligand is neutral, or it might be negative also, I mean whatever be, but it has a definite thing. So it is either negative one or you have a ligand one. Now after the formation of complex, if it retains the same oxidative, or I mean let's say we actually term the innocent or non-innocent depending on the fate of the metal oxidation state. So you have a metal in N2 plus and the ligand is approaching. So ligand may be positive, neutral, ligand may be uh, anionic. So no problem. So now it has bonded to the N2 plus. So after the formation of the bond, if the 2 plus charge retains solely on the metal, then you will say that ligand is non-innocent. But if you see that there is a change in the metal oxidation state, definitely for innocent and non-innocent, it doesn't go from +2 to +3 completely, but there are intermediate like 2.5, and you can measure from this that this is the way you can do it. So then you say that it is perturbing the existing metal oxidation state, and then you will call it a non-innocent. Is it clear?
Ma'am, for the neutral ligands, when we suppose we take the CONH3 whole 6, something charge is there, but when we try to calculate the charge on the metal, we take the contribution from the NH3 to be 0 and just put the charge over the cobalt like that. So in that case, the NH no complete charge is upon the cobalt. So
So you
is
just
it
do the EPR, electron paramagnetic resonance we do, right? So there are
okay?
techniques. So you cobalt 3 plus means cobalt is D7 system, right? So cobalt 3 plus means D6, right? Now D6 you have to consider too many things that will come during the, so if it is a NH3, so this is a weak field again, right? So you know that how many unpaired electrons are there. So from that unpaired electron, you have definite. If you have a definite cobalt 3 complex, you know that how many unpaired electron is there, and you know what is the exact character of EPR. Or if you can do the magnetism, right? Then if
Okay.
you do in your new compound, if you have a other ligand L, and if it perturbs this oxidation state or all in that way, so in that case the electron density is a little more towards ligand, and the metal oxidation state, if it oxidizes and if it reduces differently, so these EPR signals and this magnetism value will be different.
Okay.
Okay, so that thing we will. I mean, you can, once you know the bonding and these things, then you will understand easily. I mean, I don't have to make you understand that these things happen. Okay.
So apparently the thing is that we can't do it on pen paper and we have to go through APR and those techniques to
Yes,
determine that.
because yes, you can go through the pen and paper. You can't tell this is an innocent ligand or it is a non-innocent ligand. And also, I mean, it also depends on that particular metal, how hard this metal. I mean, you have read this. I think in 12th also, this metals can be categorized like metal A category, B category, and in between this A and B category, like there are hard metal. If you just there are too many metals, right? So if you just think of, I can just give a little examples, like if you think of the metals, I mean the S block metals and the metals left to the transition metals, so the metals situated in the left, then you will say they are hard. So they are hard in the sense that they like the hard ligands. And if you just go to the very right side, to the P side, I mean P block side, then they are soft metals, right? They like sulfide ligands, more stable like this. And then if you go through this let's say palladium, platinum, and these things, uh, and go down a little bit, then they are borderline. I mean, they can well bond well to these hard and as well as the soft also. But if you just think of this platinum, I mean, I'm just giving one example. Like if you have a platinum and you have a chlorine bond, platinum chlorine bond, and if you bring a sulfide ion like platinum, why platinum is so much this prone to this biological thing, because you have the amino acids, the cysteine and all. Again, you have these other amino acids, and I mean DNA. You have the nitrogen. So platinum Cl bond is very easily labile. I mean, there is the concept of lability, right? So that again you will learn in the reaction kinetics, that there is a bond, platinum chlorine bond is there, but if it gets something, it prefers to bond with that one. So this hydrolysis we do. I mean, if you read any biological paper like with platinum chlorine, so in every case you will see that there is a report that this is the hydrolysis. So this platinum chlorine bond is the strength of the platinum chlorine bond is first uh, 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 decided by the hydrolysis value. I mean, how easy the hydrolysis is and how difficult the hydrolysis is this, and then it is subjected to the biological work, so that I mean, I mean, if you see that at that particular, because there are two chlorine platinum chlorine bond and there are two other uh, ligand, and also this strength of this platinum chlorine bond to some way depends on the other ligands also, because how much do they electron donating or they are electron a little bit withdrawing, depending on all this. So there are too many parameters that actually work, and then depending on that platinum chlorine bond, actually you can do this. I mean, you can say this. I mean, I can give you one example, but I shall not write it. It is specifically from the research nothing. Like if we have a dipyridine ligand, like three nitrogen a pyridine ring, and that bonds to the platinum, and the fourth bond platinum is with chlorine, then that platinum chlorine bond you can easily break. And in that case, the T half, I mean, the reaction is very easily, very facile. But if you take a platinum bipyridine, let's say, platinum bipyridyl, and then you just put chlorine, or if you have the S and N ligand from the platinum, you are taking any ligand like it had sulfur bonded, then breaking this platinum chlorine bond is very difficult. So these things are there. I mean, that you cover, we will cover in the bonding. Okay.
Okay, ma'am.
Okay, so let us come to the stereoisomerism and then this diastereoisomers. So what is the stereoisomers? Again, I shall ask you people. I mean, let me listen from you. How much do you remember? It is very easy, but we will go a little quickly. So please tell me what do you mean by diastereoisomer? So it is there. So you know that, but what is your idea about diastereoisomer and enantiomer? That you just tell me, then I shall proceed. All of you know. Please don't hesitate. You just tell me. Please, what is diastereomers and what is enantiomer? So what is your idea? So let me ask you that will the bond connectivity, so let's say you have M L1, L2, L3, L4, right? So will the bond connectivity remain the same and what is the character? Quickly. I know you have read this. Tell something, even if it is wrong, you just tell. If you are not confident, just recapitulate. If you cannot tell, that means you have forgot. It's not that you have not understood, right? Quick. Okay, please tell me quickly. What is diastereoisomer and what is enantiomer? What is your idea? What is stereoisomers? How do they differ, a diastereoisomer or enantiomer? Okay, enantiomers or stereoisomers are non-superimage mirror image of each other. So, Shishira, so in that case, what you are writing, so it means that the bond connectivity remains the same, right? Okay, I don't want to waste time on this. So fine. So now that the this is the uh, a type of definition. So this is the same empirical formula. So if you have the same empirical formula, that identical coordination number and basic set, and display the same atom to atom bonding sequence throughout. This is very, very important. But in which the ligand atoms differ in their locations in space. So this is the stereoisomer. So if a MA4 ligand, if I write that M is in the square planar, this is also a, sorry, not A will not be. Oh, okay, this is also a type of isomerism, right? So one is the square planar and another is the tetrahedral. So they are stereoisomers. Will you agree? Will you agree if I say that these two are stereoisomer? Yes or no? Okay, screen is not, sorry. I forgot that. Now you can see. So there are, so again I am telling that stereoisomers, if I just say the stereoisomer, when you say stereoisomer, all of you know that same empirical formula. This is the point. Identical coordination number and basic shape, right? And display the same atom to atom bonding sequence throughout, but in which the ligand atoms differ in their location in space. So in that case, my question was that if you have a MA4 and if you have a MA4 in this square planar and in tetrahedral. So from this uh, uh, definition, would you say that these two are isomer, stereoisomer?
No, ma'am. No, ma'am.
Okay, so why? So which one, which point? So it is not, the basic shape are not same, right? Okay, so let us go to the again the diastereomers. Then all of them are diastereomers. The general class of isomer. I am going a little bit fast because these things you know, and many more difficult things you have to learn. The stereoisomer include geometric isomers. So this is called cis-trans isomer. So geometric isomers are called cis-trans isomerism. You know, and any particular diastereomer, all of you know, is an enantiomer when you have the mirror image relationship. This is very important. Just remember that it has a mirror image relationship is considered. That's it. I mean, it's very easy. We will not go. Is considered. Okay. So it is that not all compound will exist at two mirror image forms or enantiomers as the property related to the symmetry. So symmetry will come, we know, you will know the symmetry. And diastereomers are not the same thing as enantiomers. So these enantiomers themselves are diastereoisomers in one sense, but they are not the same. So here the complex to have enantiomer, they must have either asymmetric, right? Asymmetric uh, or dissymmetric. These terms maybe you know. I shall, if it is not you have any problem, I shall just tell you one day, next day. So rotation reflection axis, I mean if you have something name M A B C D, first you do the rotation. So M D B C A, and then you do the reflection. So then it is called the rotation reflection axis. You know that, but I shall explain again. Okay, so now a molecule that is asymmetric or dissymmetric is called a chiral compound. You know that chiral compound. So this chiral compound, one of the basic point is that the all the molecules that are attached to it in some way different. So 1, 2, 3, 4. So they must be different. So if it is a tetrahedral compound, or if it is a octahedral compound, then it is not necessarily if you that the compound must be different. Like if you have MEN whole 3, then it might have enantiomer, though the three molecules are En. So where does it difference? So this is the main difference between organic isomerism and inorganic isomerism. For organic isomerism, as we considered the carbon and as we considered there are 4 bonds, so there the 4 moiety must be different to be chiral. But in inorganic compound, as you have chelate rings and different chelate rings, I mean if you, even if it is MEN is not 3, if it is a ML and this L is a hexadentate ligand, L is hexadentate, then also you can have this chelate, this chiral compound, because there is a mirror image relationship. One mirror image is not superimposable to the other. So this is the point. And in that case, the compound will show the optical activity. And as you know that optical activity, what is it? It is very simple, that if you have a compound which is chiral, which is asymmetric or disymmetric, and it is, if you take the enantiomers A and B, and they are optically, they will rotate the plane of polarized light in different directions. That is the main thing. So this is the uh, uh, main point to understand the optical activity. It is very easy, and I shall not explain it anymore. And if you read it, it will be easy to you. I mean, it will be very easy for you to understand. So, but diastereomers, again, diastereomers are not optically active, and uh, I mean, they are chemical and physical properties might be different, because I mean, mm, how I mean, if you take a cis and trans isomer, as I can say that this chemical we have already explained, right? That how do it bond to other compounds? So this is one of the chemical property, and in also physical property, like if you take this MAA and BB, and if you take MBB AA, then if you have a dipole moment for these molecules, and then this molecule will have dipole moment, and here the dipole moment will be cancelled. I mean, it depends on the effective dipole moment. Considering all the molecules, it will have, so this dipole moment, and then this melting point in some cases. Melting point not that much, but a little bit, because this trans effect is there, so the molecule becomes more stable in case of this diastereoisomers. And then you have these properties different, but in enantiomer only they differ in the ability of rotate polarized light, because they are the molecular strength remain the same, right? So if you just have this okay, I cannot. So these are the example for 4 coordinated, and this is for 6 coordinated cis and trans isomer. This is very important. Now, I have written it there. So if you have, now we'll just consider. So this is a calculation you have, and you can find it in a book. That if you have a square plane, this 4 coordinated complex, so isomerism, diastereoisomerism is very important for the square planar 4 coordinated. So it might be MA4. So if it is a MA4, then only one isomer definitely. If it is MA3B, then also it is only one isomer. If it is MA2B2, then you have the two isomers. And if you have MA2BC, again you have two isomers. And if you have a MABCD, sorry, if you have a ABCD, then also you have isomers, different isomers. Not only diastereoisomer, but how many isomers it might have. Then you can have these 3 type of isomers. One is this one, so this one again, and if you have the tetrahedral, then you have this type of this enantiomeric pair. And then also you have a change, like it could be m you can calculate it, how many can you write, d and d, right? So this could be the, and another is that you have a d is opposite to the, right? So these 3 isomers, and then you have the enantiomer. And if you again have the this trigonal bipyridine, then you have the, here I have mentioned these two. Like if you have a then you can go to the mx. So these two, I shall give the explanation during the bonding also. So these two are called sometimes. Have you read the term fluxional? Have you know the term fluxional?
No,
Any?
ma'am.
Yes or no?
No, ma'am.
No, ma'am.
Okay. So the fluxional means, so let me explain that stability of a complex. I mean, when you will run the bonding, when you learn the bonding, then if you have a metal and if you have, let's say, five ligands, if you have a metal and if you have a five ligands, then how would you define? So there are two possible geometry for this five member ligand, like here two possible geometry, sorry, two possible geometries, let's say that I am writing. So there are two possible geometry. So how do you know that you are, uh, I mean, how do you know these two things are, I mean, which one will it adopt for a set of metal and ligand? Which one will it adopt? The first question. The second question is that if it adopts a particular one, then why does it adopt that particular one, right? This question really comes. So what happens in case of, in most of the cases of this five membered ring, so this difference of energy of stability with any set of metal and ligand, in most set of metal and ligand, these two are not very high. So if you are in a solution, a compound is in a solution, then both of them can interchange between these cases, these uh, positions. And how do you know? Here you need the NMR spectra. NMR spectra actually helps you to understand whether the molecule is in one particular this environment or it is changing. So that is a little complicated, that I am not. So these molecules are called fluxional molecules. So, and when can you get them in a very stable position? If you go to very low temperature, like minus 77 K, if you go, then you can freeze one of them and you can freeze this fluctuability. But in room temperature, just from the environment, it will take that small amount of energy and it just changes it, right? And then these, there is a rotation, like this is coming to here and this is coming to there and this is coming to, in that way there is a rearrangement, and this is called very pseudo rotation. So these terms, if you learn, it will help you to understand things, I mean other things also. So this is called very pseudo rotation. So I do not know what also. So these isomers I have given, so you just read it. I am not explaining it anymore. What is the time? So it's already 10:22. Now my, uh, I can show you later. Sorry, whatever I wrote is gone. Okay, no problem. So these are the things that I have written. You can, all these things are written because whatever I told you in, and also you, I think it is from Silver Atkins, so you will get all these things. Okay, here you can see that these are the energies of this. I shall explain a little bit. Okay, this part I shall explain. I have already explained you that complexes are often highly fluxional because this axial at one moment and equatorial the next moment. You read it, please. You read it. This particular slide of the isomerism, you please read. And if you don't get anything, if you don't understand anything, please come back. Please, I shall not explain. I mean, I have to go to a very deep, little bit deep. And then this is the octahedral. Everything is written. One thing I shall next day explain with all these Fachmer isomers very well, because Fachmer's isomerism is very important, and this is you have to understand. I mean, how do you understand Fach and Mer? This is very important, and here you can get that how many isomers you have with all this is, and again this is the this lambda and delta. So these things we will explain next day. This lambda, delta, and this factor. Now let me come back to you and tell you the plan. Okay. So let me tell you that next Wednesday we will have a quiz. Right. So the syllabus of the quiz is for 10 minutes. And the syllabus is till the cost diagram. So anybody has any question, anything? Otherwise, I will just sum up what we have learned today. So if you have any question till first diagram, please feel free to ask today, or you have this Monday and Tuesday classes, and also you can write a mail. You can in WhatsApp also you can write, but for WhatsApp and mail you may need to wait a little bit, because whenever I shall get time I shall tell you, or in that way I can explain, or you just wait till Monday, I shall explain. And what is the type of question? I am clearly saying you don't have to remember the correct answer in that way. What you have to do is there will be quiz, so there will be four options, and definitely one of the options are there. Like the first diagram, you do not have to remember that where the copper plus is there and where the copper 2 is there, or where the copper 0 is there. So I shall give you, let's say, the diagram, and for that diagram you have to answer the question. So you will have uh, the answer within the question itself, but you must know that this is the point that you must know, right? So do you have any question? Okay, you think of it. Let me summarize this. So what did we learn? So we learned that for metal ligand complex formation, you have the metal and you have the ligand. So once you have the metal and ligand, the stability of the complex depends on the metal, stability of the complex so stability of the complex depends on the metal, definitely the metal ligand bonding, that we have not read, because that we will take care in the bonding in a very detailed manner. And then the chelate ring effect. So when you are taking a ligands, the ligands can be of different type. Ligands can be of monodentate, bidentate, and hexadentate, polydentate, anything. And that ligand structure also tell you that how much will be the stability of that complex. Now you have learned the chelate effect. So what does the chelate effect actually consider? The chelate effect consider that entropy part of the molecule, and also that gives you the stability. If you take this for stability you need the del G value, and del G value depends on the del H and the del S. Now the chelate actually can take care of only the del S value, but the in case the other things remain a little similar, so that del H value doesn't contribute too much, then the chelate effect is really prominent. But there are cases where the chelate formation also could not stabilize because there is a huge difference in the in the crystallization or in the other parameters. This bond length and all these things. Now, if we particularly put at the chelate, then the chelate have two different things. One is the bite angle, and this bite angle determines the stability of the complex in 5-membered or 6-membered or 4-membered or 7-membered. And considering this, what is the most stable? Generally, 5-membered chelate ring are the most stable, right? And when the 6-member rings are stable, when you have a conjugated ligand, and like the this benzene molecule, it has a conjugation throughout involving the metals that we have learned. And as an added things, we have learned the terms non-innocent and innocent ligand, where the ligand also involves itself in the uh, I mean the oxidation states of the metal. When the ligand part of the oxidation state of metal, then we tell it as the non-innocent ligand, and when it doesn't perturb the oxidation state of the metal, then we say it is a innocent ligand. That's it. And then we have started the isomerism, and isomerism is very easy, except you have to understand very well the enantiomeric part with this Fakmar isomerism and the lambda and delta isomerism. So these two isomerism I shall explain very well in I mean not very well, the with my capacity definitely. If you do not understand, you will again ask me. And these are the uh, two isomerism is very important. Other isomers are easy, but there is a formula and you can write it well. And there are, if you can, for a particular things, if you can write 6 different isomers, which one will be stable, that you can understand once you read the bonding thing. Otherwise you will not understand which one will be more stable, because only the trans effect actually in that case works well. Okay, and also that which ligand is approaching from the z axis and x axis and y axis. Okay, so do you have any question from first diagram? So now as we are progressing from the next day, we can go a little bit more on the Thursday also. Today we can finish it here. So I can assume that you do not have any question, right? So just think of it, read it, and then if you have any problem, or if you just want to that what are the type of question, that also I shall can discuss on Monday. So please read, take your time.